So, hello, good evening for the last talk today. I'm sure everyone here wants to go to the dinner after this. So, yeah, I'm working as I'm a consultant at Khronos and as developer technology engineer at NVIDIA in machine learning for professional visualization. So we are quite interested in the edge as well because we have ISVs like Adobe who want to ship their machine learning models on the local system. And well, it's a good combination because as I'm a council chair, I'm interested in what customers want to do. And Khronos, NVIDIA, has a lot of customers who want to ship AI, so I can talk to them about their needs. And so within the ML Council, we started to a research project, which I talked about this morning, about what do people really need from Khronos to achieve the best possible edge AI deployment if they use Khronos APIs. And the findings were like achieving speed of light is really hard and it requires a lot of manual labor. Like we have seen talks today where they talked about, okay, we have to implement GEM and we might need different implementations for different platforms. And so you have to optimize for every platform, for each shader type. It's an endless endeavor. You can have a full-time job, multiple lifetimes, just implementing GEM. And even if you're implementing shaders in all those shader languages, or Slang, hopefully now, still performance portability is not given because yeah, you have different cache sizes, you have bandwidth, shared memory size, subcode sizes, and if you're using an operator library, then still some operator libraries are faster for certain operations than other ones. So you lost again. If you just have a standard model, you have to run a special optimizer for your target, like we've seen today with Optimum, where they added an optimizer for the given target for the graph. And yeah, now you're optimizing for platforms you know. And this is okay if you are on a device you ship. Like if you're a mobile phone vendor, you have your mobile phone and you want to ship one specific AI on one specific mobile phone, this works. But now you're a developer of an application generating images and you want to ship it on a mobile phone, but you don't know which mobile phone a user will use. So what do? And you will have multiple mobile phones per month which come out, which might have different chips, and then your application will run slow or won't run at all. It's not really a good use of resources relying on so many different APIs to get to machine learning. And yeah, as Khronos, we develop open standards, and we also have open source projects like Slang, and we try to combine them. And yeah, can we develop an open standard which can be implemented by a driver where the graph is passed to the driver, but at the same time, where we can provide an implementation of this standard which runs on compute, so that you can have a single standard running on drivers if they support it, or running on compute if the driver doesn't support it, so that you can get the maximum reach within the ecosystem, but with only a single API. And well, if this implementation running on compute would be good, and a vendor wouldn't have to implement anything, but if a vendor says, oh, I have a special piece of hardware for one operation, then you could maybe implement this operation and keep the rest of the API. This is the idea which came out of this research project and which seemed to be interesting for what I heard today as well. So the solution exploration we came to was, okay, can we develop a vision within Khronos and then validate it in the industry if it's a good thing or not to do? So in the past, we had compute shaders which used Scala mass only. And if you had Scala mass only, yeah, you had a lot of instruction, a lot of loads. So we added tensor cores, and I will get to more details in the next slides. So tensor cores increased mass throughput a lot, but then you still have performance portability. So the next evolution, which already happened within Khronos for one vendor, was introduce a compute graph into Vulkan. And this way, you get a unified driver for this GPU and NPU, if the same vendor has one Vulkan driver for both. It's ideal. You don't care anymore if you go on NPU or compute. It's a single driver, single interface, you're done. But then we are back to custom operators, like, yeah, you have to implement them, they're a pain. So at some point, we will have to add compute shaders, which can run within the graph with all the shape inference. And then we are back to performance portability problems. So we will have to add a tensor language, which is independent of the underlying hardware as much as possible. So because low level is my thing, I want to torture you a little bit about why did we add tensor cores to hardware. So if you implement a gem, most famous operation of all, each thread on a GPU would compute one element of C in the worst simple way. So you would have to do 2 times k loads, where k is a common dimension, and k fused multiply add operations as well. But for loads, you would have to do 2 times k times m times n loads from memory to get the data into registers so that you can do the math, and in total m times n times k FMAs. It's a huge mess for memory and for the number of instructions to be executed. You will be limited by the clock. You won't be limited by power unless instruction decoder is too expensive. Yeah, but it's not great. With cooperative group math or tensor cores, a group of threads jointly works together and gets the data for A and B only once. So assume you have like 32 threads and they work, or 16 is maybe easier, 16 threads working on a 4x8 by 4 matrix. Yeah, then you can load, each thread could load one item of A, one item of B, and send them to the tensor cores and then do the math, so, which would be a single operation in an ideal world. So you have m times n loads only, and just a single tensor math operation. So clock is no longer your enemy, because for the whole matrix, it's just one operation. And for the loads, it's also a big saving. So you have only m by, you reduce the number of instructions executed by m times n times k divided by group size, and the loads by 2k. So tensor cores are awesome, and well, with those you are most likely getting energy bound. But yeah, all of the stuff is still limited by what is the dimension of the tensor cores, how many shared memory do you have to cache stuff, what's your cache size, how big of a tile do you put in a single warp, so many decisions. So we want to have a compute graph in the driver so that the driver can decide how to implement a gem. The only instance which really knows the platform below is, to be honest, the driver. It knows, so if a new generation comes out, all the open source frameworks in the world won't know about this new generation today. So they will have to be informed upfront, and then they will have to get pre-release GPUs if they are lucky, or mobile phones, and then optimize and implement, and the libraries will grow and grow and grow and get more and more unmaintainable, potentially, because you're adding more and more platforms in the future. I think it's very better if a full graph would be visible to the driver, at least as option, that a vendor who is interested in getting optimizations like fusion tiling and platform optimized kernel can decide to do so, and does it only once and not in each and every framework. So if you are an IHV and you have 10 frameworks you have to support, you need engineers for all those 10 frameworks to support those to implement the new GPU generations again. It's a lot of waste of manual experts. And also it simplifies the development, because now you have only a single hardware abstraction layer for all the many different NPUs and the GPUs. But having the compute graph, we are back to which operators are we going to support, and the operators that will always be outdated, because The driver will ship every once in a while, and new operators will come out way more often. And if you have on mobile phones, the driver might never get updated on your mobile phone at all. So what do? Yeah, introduce custom operators. So this is a vision. This will be discussed at Khronos, and I like to get feedback about if you would like it. For the compute graph, we want to add compute shaders, which have shape inference information, and this will bring you back the custom shaders, but this won't solve the problem of performance portability for those shaders, and they might not be fusible because how they work. Maybe we find ways to make it. But still, now, if you have a new operation you want to support on an old device, you have a chance to do so by adding a compute shader. Or if you have a framework which just generates the compute graph, pass to the driver, and the driver says, I don't support an operation, you can always implement a fallback compute shader to bring the operation to the device and not decide to not to support the device at all. You can support it with slightly limited performance. I think it's a huge gain. But in the final stage of the vision, the idea would be to define a domain-specific shader language, which doesn't know about shared memory, cache sizes, subgroup sizes, number of processors, SMD risks, nothing, which just gets the definition for the tensor itself, how to compute it. And this way, the compiler of the tensor language knows about shared memory, the cache sizes, register limits, anything. And the application can avoid to use specific extensions. It might or might not yet know because new ones are getting released frequently. The compiler could use the latest known extension and then bring the best possible implementation to the device. Or it could even decide to use special hardware implementing those. And if we're going to go this way, it's unlikely that each and every vendor will have an implementation of this new potential standard we are discussing. So Khronos is thinking about having an open source implementation. So Khronos started to do open source project, for example, with Slang, for the standard, which would run on compute. I mean, this still would have all the problems with compute up to the point where all IHVs optimize their kernels within this library. But at least it would be a path building up an ecosystem around Vulkan in this case, where Vulkan could be a good, viable, and efficient target for machine learning inference. And the goal would be that it can run on every Vulkan's capable device, meaning the scalar mass, but that it also knows about cooperative matrices extensions and maybe even have special implementations for some vendors which go further, having more extensions to make those vendors efficient. For the extensions released by ARM, for graphs, for Vulkan, there is such a layer, but this layer is just for functionality. There isn't any optimization yet. And it would be great if the ecosystem could evaluate it and think, this is a really great way to go. Khronos, please do something, or hey, we are going to help you. So my question to the audience is, do you think this is the way to go forward to break the HANGZHOU problem? Because if no one would use the standard, we wouldn't define the standard. And then we can't argue that someone should do something at all. So we need to have some feedback if you're interested in it. And would you rely on such a layer? And would you really request the layer to be the fully fledged optimizing master compiler with the risk that it gets larger and harder to ship on mobile devices because of size, or something small that just does the job as good as possible? And for the tensor language, how would it look like? It turns out that one group within Khronos, the NF group, secretly enhanced NF from just being an operator language, which wasn't that impressive, to an scripting language, to a domain-specific scripting language to describe tensor operators and the graphs built from them. So NNEF itself is just a framework where you can define tensor operators. And you could define any tensor operator set you imagine. You could have NNEF operators, MLIR link algorithm operators, Tosa, whatever you want. You define those in the scripting language. So the focus is really having a language instead of an operator set like before, which will be outdated quite quick because some researcher decides we have a new, more awesome operation, we need to write custom shaders. Now they could do it in the scripting language, and a compiler could compile it as good as possible to the underlying hardware. But with scripting languages defining operators, at the same time, a driver could decide, I know this operator. And it can verify that the script does exactly what the driver expects. And the IHVs could provide a specialized implementation, if required, which runs as fast as possible on the hardware. And it would have to do this only for operators which are complex. So there's no need to have a special implementation for ReLU. It's simple element-wise operation. Yeah, and this really brings us to custom operators in a way where a compiler could compile to any architecture with any extension, or the compiler could reside inside the driver to be as efficient as possible for the platform. And it turns out that the NNEF tools GitHub repository, there's a QR code on the right, already contains a TVM-based sample compiler. It's not tuned for performance, just for functionality. And it has a Vulkan, CUDA, and CPU backend. And there's also the NNEF2 specification available as pre-release. It's not yet finalized. So if there's anything in the specification which isn't great, it would be good if people take a look at it and give us feedback before we make a final release. And because this was quite dry, here's some quick operator definition for a matrix multiply, showing how simple it is to define. Yeah, you are defining inputs. You can use symbolic names for dimensions, and the compiler matches all the dimensions between input and output for shape inference. And at lowering is the actual code definition. So the first line, Cij equals 0, just initializes the matrix to 0. And the output is the whole index space from I and j between 0 and m and n. So all you are defining is an index space and operations to run on this index space. And then the second line does accumulate the dot product over another index space. And that's it. Einstein some notation. It's in the middle of hard to detail. It doesn't require any low-level coding expertise to write. And assuming we can make a good compiler, we can target scalar mass, cooperative matrices, some extension we don't know. And at the same time, because operator matmul has a semantic definition, we can also have an NPU support for matmul, where the NPU ignores the code, assuming we have standardized the operation, and then just does a matmul on an NPU. And for the whole network, another example where you can define a graph, in this case an AlexNet, it gets an input, output, it has a lot of variables, and then, like you know from PyTorch, just a few set of NN operators. So that's it. So get involved if you're interested in this. Feel free to participate in Khronos open source projects like Slang or NNEF Tools, the compiler. Please take a look at the NNEF Tools project, check it out, give us feedback if it doesn't work for you, if it's slow, if it's bad, if it's awesome, we are happy as well to get feedback. We are wondering if you need to add more compiler targets or not. And for Slang, Slang is our open source shading language. Would you like to see support for graphs in Slangs? So the whole graph support will be in, so the plan is to have the whole graph support in SpirV. And Slang is a compiler which can compile to SpirV. So we could do everything we showed in SpirV as well. And then you would have a single ecosystem within Khronos coming from a SpirV shading language where you can have compute shaders for custom shaders. In an ideal world where you could define those script ND shaders in some way, which isn't defined yet, and define your neural networks as well, and then compile it to SpirV or maybe to CPU or whatever Slang supports.